So this is the end of a wonderful couple of days. I have had a great time. I hope you guys have as well. I stand between you and perhaps your flights and maybe a dinner. It's really these guys. This panel is about how Gen AI really feeds into scientific engineering applications. Really, what is missing? What are opportunities? What are challenges? And where we might be going right or wrong. So the hope or the way we set up this next 45 minutes or so, we'll start with maybe a 2 to 3 minute position from each of you. Please do keep it to 3 minutes so that we can all have a fun time chatting at that point. I have a bunch of questions that the organizers sent to me, and we'll go through those questions, and then hopefully we'll spend more of the time having a conversation and getting everybody's feedback on sort of bringing this whole thing together. So if I may, please, do we want to start from that side? Let's take 3 minutes, and I'm not going to monitor the 3 minutes. I'm going to assume that you guys will take 3 minutes, and we'll go from there.
What trust?
Okay, great. Shuiwang, Professor of Computer Science, Texas A&M. So I work on AI machine learning. So I work on actually on deep learning a long time ago. I work as a student. I work on deep learning for video action recognition in 2009. So and over the years I have been working on one hand we work on fundamental machine learning problems. On the other hand, I'm very interested in science problems, especially in physics, quantum mechanics, density functional theory, quantum chemistry, and physics simulations. For example, fluid dynamics, air dynamics, how to simulate combustion, propulsion, detonation, etc. This a mechanical or aerospace engineer type of problems.
Just to be sure, my hope was that you would take the 3 minutes also to establish yourself as it relates to the topic of the panel, which is what are the opportunities, challenges, and the general area of Gen AI as it relates to science and engineering.
Yeah, great. I think my view on this generative AI, for example, most people talk about the GPT type of models. And for example, this is just next token prediction. We know that this is not new, right? People have been doing next token prediction since 1950s. So this is the problem itself is not new, just because we try to model the probability distribution of a sequence of tokens, and just by the very basic product rule of probability, this can be written as a condition of predicting next token. And I think it's just because we have more data, we have more powerful models, and we can model this distribution more accurately. So I personally feel, all the problem, or at least most of the problem that face traditional machine learning is still here. For example, so we want to, in machine learning, we study auto distribution or causality, etc. This is extremely difficult for me, Machine learning is very good at doing interpolation, right? But out of domains and extrapolation, I think, and the causality, for example, this is, to me, this boils down to the same problem. Can you learn, for example, if you have observation, you can learn the true causal rules. This allows you to deal with problem in very different domains. This naturally allows you to do OOD, right? So I think for machine learning, this is going to be extremely difficult if you only observe, if you only rely on observational data, and you have to make very strong priors of data. For example, there is a structural causal model. You have to assume there is a structural causal model that have generated data, then you can infer the causal rules. So if you do not have a prior assumption of data, and if you only rely on observational data, I think this is going to be hard, very hard. And I think the same thing applies to this GPT models. If you try, I think they are very difficult at doing OOD and causality. Another thing is that people have been talking about, reasoning planning. I think I touched on this a little bit yesterday, but I think the question here is really, people are talking about this AI scientist, how to build an AI agent that can help formulate scientific hypotheses. Right? This, I think, require reasoning and planning capabilities. And can you imagine that next token prediction can lead you to a reasoning and planning capability? So I give you two simple examples yesterday. Very simple, reasoning and planning problem, and the GPT failed completely. I think it's very good. I think my point is it's very important to understand what it can do, what it cannot do. Thank you.
Thank you.
Thank you.
Tanya.
First of all, I want to thank you all and that for staying and for being still engaged and awake and for providing us with an audience for our pontification. So thank you very much. With this, so I'm Tanya Berger-Wolf. I am professor of computer science and engineering, electrical computer engineering, and evolution, ecology, and organismal biology at the Ohio State University, the Ohio State University. Recently, the part was in a New York Times crossword as the article that was copyrighted by the Ohio State University. So anyway, I have a variety of other titles. Most relevant for this context is the one that you've already heard, is the director of the Imageomics Institute, NSF-funded Harnessing Data Revolution Institute, as well as several others. So I've already said some of the part of my position on what is, so what's a good, generative AI scientist doing in a space like knowledge-guided machine learning kind of stuff. What can we do? What is the value added of AI in general for science that we've talked about a lot yesterday, and particularly generative AI. And we saw a beautiful example that is, I'm super biased about, in imageomics of using phylogeny as a guiding structure to generate potential examples of ancestral phenotypes, right? Of what would ancestral species of fish would have looked like, or literally generating examples of what would perturbations in some of the part of the traits produce potentially down different lineages of evolution. So these are hypothesis generating approaches using generative image AI, right? Not ChatGPT by any means. And we've taken this in imageomics a lot further. So you can use generative AI by transitioning, so you can train not on evolutionary knowledge and evolutionary structures, but on genetic, for example, for bird egg phenotypes, and then literally kind of interpolate and between two phenotypes of two nests of bird eggs, look what would they look like, and then 3D print kind of as you're walking along between the two nests, 3D print those egg phenotypes and literally ask the birds, would you accept it as one of yours? Would you accept this as one of yours? And start drawing the isolines of kin recognition and kin selection, right? Understanding that. This is what generative AI allows us to do. We have a whole project on using generative AI to understand mimicry in butterflies and connect phenotype to genotype directly. So in all of these examples, there's a commonality, and we're using images, the generative AI in the image context, is that we're using it to generate hypotheses, right? Something that does not exist for different various reasons of limitation. And the beauty of doing it in this context is that, one, we can present that something that doesn't exist in nature, or maybe it's hard to kind of get in nature for various reasons as part of data collection process. And we can test these hypotheses, and this is what I love about the setting, is by looking at the world through the eyes of other species, through the senses of other species. We can ask the bird, do you like this egg? Even if we cannot, I cannot tell the difference between the eggs from this nest versus that nest. What do I know, right? But the mother bird definitely can. I don't know about, what ancestral species of fish may have looked like, but we have good methods to test. And maybe that proposes, that hypothesis is a new set of traits that we may have completely overlooked to understand the evolutionary processes, and maybe the connection to changing environment, as was pointed out. Maybe we can use that to understand the mimicry in butterflies that for us, the human eyes, is completely missed, because that has not evolved for the benefit of human eyes, but for the benefit of birds' eyes, the predators, right? And we can literally then, when we have these hypotheses, we can print these butterflies and ask the birds, would you pick this one over that one? Would you eat this one? So these are the kinds of exciting things for me that generative AI opens up, is both but it only works if we change completely the framework of how we do machine learning. And I talked about it yesterday, and I'm happy to repeat, we need to change the metrics. We need to change this whole notion of accuracy, evaluating accuracy, the very specific set of metrics on benchmark data sets. We need to, so Joseph talked about, and several other talks mentioned, very different metrics, very different notions of how we evaluate these algorithms and what data sets we use, and how we then use these approaches to answer which questions.
Thanks, Tanya.
Like 3 minutes.
So good afternoon, everybody. So I'm Wei Ding from UMass Boston. So I'm a professor of computer science. And first, I would like to thank the organizers of this workshop. I'm really impressed by the diversified speakers of the workshop, and also the quality of the presentations by the workshop, and including the questions asked by the audience. So because actually I'm supposed to be in the EJCAI to present the papers before I knew we had this workshop. Then I think Weiping and Shashi has already established their credibility. They can always deliver great workshops. So once I knew that they're going to have 2 workshops, I immediately changed my airplane tickets. And so came here, and I think I spent 2 days here, and totally worth my time. So I really enjoyed I'm actually very surprised to hear the presentation from the speakers at different levels, and how inclusive the workshop is to include speakers from all different backgrounds. So I have learned a lot. So this is an amazing event. And then, so I began to get connected with the spatial temporal data mining when I was a PhD student. And actually, at that time, I read a book written by Shashi Shikha on spatial temporal data mining. And I had a question about one formula of the book. So I, as a student, I wrote an email to the author and asked, okay, what does this mean? And to my surprise, I get a response within the same day. Okay, so that indicates how responsible, reliable, the top researchers are. And also over the years, I observed how Weiping and Shashi has done really good work in the, all kinds of, applied data mining AI algorithm to many important real world applications. So, and then to quickly finish my part, I think for the foundational KGML models, and then because since I joined UMass Boston in 2008, I began to do my research with machine learning algorithms on many different application domains. And then, to be honest, it's mainly driven on where I can get the research grants. Okay, so I started with several NASA grants applications, get awards. So I'm working on the Mars data. Okay, so we studied the Mars soil data. We studied the water on Mars. We also studied how the impact craters distributed on Mars. Then later, unfortunately, the research program of that NASA was canceled. Okay, I no longer have money. So then I have to see, okay, in Boston, what should I do? So I think that I should change to AI in health. So I began to submit proposal to NIH. Then I have collaborators in Dana-Farber and in Harvard University. Then we began to study data on the mutate, genetic data sets. We're working on the cancer subtyping, and then we're working on facial activity classification. We're working on the, try to qualify the pen. Okay. And then now what I'm working on is we also work with the Boston Police Department. So we started the crime data. So I have the opportunity to work with all different kind of domain experts and then study all different kind of real world problems at different levels. So my understanding about the challenges, opportunities for the foundation KGML model is, I think the first one, even is going to be, you have to do knowledge guided, okay, machine learning, data mining, but it's also quite important. You still want to have high quality, accurate, annotated data set. So this is actually very important. And also I found out for some domains, you have abundant data, for example, remote sensing areas, right? And then for the medical domain, the data often quite sparse. So how can you handle this? Okay, because as a machine learning scientist, you have to deal with the data set at the different level of quality. So this is the first one. And the second part is how you can integrate knowledge into your machine learning models. So what kind of structure you should use? So I think Anusha have made a great presentation in the morning, and also Javed talk about how you can incorporate knowledge into machine learning models, but in which way, okay? And what is the proper way? You really have to understand the problem domain well. However, we're computer scientists. Okay, so the next one I'm going to, so talking about the model generalization, I think it's also quite important because you have to really implement models, not only specific in the ad hoc solution for this particular problem. As a computer scientist, you have to design the algorithm that can be generalized to more, widespread problems. And the next thing is about the interdisciplinary collaboration. I want to actually, I did have a concern about the interpretability. I know it's quite important for you to generate a model that can be interpreted, okay? But on the other hand, actually I have my own conservation because I think we're computer scientists, we're working on the algorithm, right? Sometimes if we design a reasonable performance evaluation matrix, and if the matrix can provide good results, even the model cannot be interpretable. However, if the results is convincing by the domain experts, that should be fine because we're computer scientists. So we're not physics, we're not mathematics. So we're not here to design new formulas, right? So as long as the performance evaluation really makes sense, then maybe it's okay. It still has kind of black box approach. I'm going to finish here.
Hello, everyone. I'm Gengchen. I'm currently an assistant professor at the Department of Geography and the Environment at University of Texas at Austin. So basically, compared with the other panelists, I'm a little bit a junior researcher. No. No, I'm thinking I'm very. This is like maybe a second panelist I have attended, so I'm still learning how to do a good panelist. Yeah. So yeah. My research is about spatially explicit artificial intelligence and geo foundation models. So I think the idea is very well aligned to the knowledge-guided machine learning because the spatially explicit AI trying to say how do we improve the state-of-art AI models, by incorporating spatial inductive bias, such as spatial heterogeneities, spatial autocorrelations, map projection, distortions, and so on and so forth. So basically, it's using domain knowledge, try to redesign the models to be improve performance on the downstream tasks. So when we think about using domain knowledge on generative AI models, I think one issue is because it is already well developed. So the space for you to change, for example, previously you can change the model architecture, you can change the loss function, you can change anything, but now you have limited space to do that. And in terms of the challenges for designing domain, so knowledge-guided foundation model or generative AI models, I think there are several aspects. For example, the data modality you want to use. So many of the tasks we have seen so far, for example, you can be multiple downstream tasks, but they all rely on, say, remote sensing images. Then it is easier for you to handle. But if you involve, say, 1, 2, 3, or 5 different data modalities, then this becomes harder and harder to develop. And also, because I'm a geographer and GIS scientist, I think that it is hard for design some task if the task is design a generative AI, if they working on downstream tasks have different spatial scale. So for example, if you're doing geocoding task, then a city is considered as a point. But if another task is a traffic forecasting, then a city is considered a network, a transportation network. So how do you develop one model to work on two very different tasks on very different spatial scale is very hard. Similarly, it is very hard to design with different spatial scope and temporal scope and temporal scales. For example, you want to analysis, you have some task for geology, which is kind of have a very long study, very long temporal history. One thing I want to emphasize is because of the nature of the domain task from different field, then it might not be, we might not think about using different evaluation matrix or different way to quantify the success of the model. For example, we know that hallucination is one of the important like drawbacks of say diffusion models. But in computer vision, the diffusion model try to do generate photorealistic images for videos, for natural images. But if we apply on remote sensing images, we are thinking about, okay, how do I apply it on, say, downstream tasks, for example, welfare intensity estimation, crop yield estimation, which is very different from you just see whether the shape is okay or the color is okay. So this is one thing. Another thing is talking about like sustainability. So one is AI for sustainability, whether the foundation models can help to solve sustainability problem. Another aspect is how can we avoid the AI model or foundation model development to cause additional sustainability problem. Yeah.
Excellent. I think we took a little more than 3 minutes each, but we'll make do with that. I did realize I forgot to introduce myself. There's one aspect of myself that I'd like to introduce. My name is Ananth Grama. I'm a professor at Purdue, but for the thing that I'm most proud of is that I'm a proud graduate of Professor Vipin Kumar's group. He's my guru. Also Professor Shashi Shekhar, many of my academic siblings, and so certainly I go way back to my roots back here. All right, so let me challenge you a little bit. So we got generalizability, out of distribution, we got spatial temporal abstraction, you know, we got validation. What I didn't hear perhaps over the last 2 days, which I thought somebody would touch on, is this notion of epistemic and aleatoric knowledge, uncertainty, what have you, the known unknowns and the unknown unknowns. So yes, we can deal with the known unknowns to some extent. So let me challenge you a little bit, and I'm sure Tanya will pick this up, and maybe others will as well. What does Gen AI do for unknown unknowns? Sure, this was not in a question that was given to the panelists, so we're putting them on the spot here.
I mean, obviously, I have opinions and not afraid to share them. So fundamentally, when we design machine learning, any machine learning approach for a domain problem, for something which is not within the kind of well-specified, here's a classification problem or something like this, the whole point is ultimately to find an embedding space where the distances and the relationships in that space correspond to relationships and distances that are semantically meaningful in the domain, right? So like this is fundamentally what we're trying to do when we're learning something that is domain meaningful. And the whole thing is, well, when we do classification or the non-foundation model, non-generative AI, we can encode that knowledge, those relationships, by giving labels, right? The supervised learning essentially enforces some of those relationships and puts in, to some extent, although we have plenty of examples when it doesn't work. When we move to foundation models, when we move to unsupervised learning and to, especially the one that ends with generative AI, but to unsupervised learning, then this explicit guidance, at least through labels, to ensure that the distances in the embedding space or clustering in the embedding space has semantic meaning is only encoded through this implicit happenstance, quite often, co-occurrences within the data. And to me, this is why it's particularly important to inject knowledge in a more explicit way into foundation models, because otherwise we're solely relying on these co-occurrences that may or may not happen. So then we need to put a lot more thought and effort on how do we actually encode knowledge with the end goal that, like, understanding that it is the relationships in the embedding space that have to have this semantic meaning, right? What is the semantics that we're going to impose on the unsupervised model? And more so, if we then are going to use this embedding space for any kind of generative process, for any kind of decoder, right? Then we better be really sure that that the epistemology, that background knowledge is encoded, that those points in the embedding space have that domain meaning, semantic meaning.
So what I was hoping somebody would say is
Okay.
that process models are good for known unknowns, whereas all of these Gen AI type models are perhaps going to give us something about unknown unknowns. So let me put it out there, and I want you to argue for or against this perspective that Gen AI has the potential to reveal unknown unknowns.
Yes, and we said that implicitly, right? That we said that this allows us to maybe generate novelty, generate something that we haven't even thought before at all. I would actually, in the unknown unknowns, I actually would advocate for hallucination, but for guided hallucination. And this is where I think the power of unknown unknowns can come to fore, to really allow us to examine through the process of guided hallucination, which I would argue all of science is like, are those unknown unknowns actually useful?
Yeah, I think I have a slightly different point. So I think we are trained, for example, let's talk about GPT. So GPT is trained to do next token prediction based on web scale data, pretty much the human collective knowledge everywhere, right? Internet. So this is trained on that kind of data and has a huge amount of knowledge. And what it can do, we ask questions, and I think that this is, to me, what this GPT model can do is approximate information retrieval. Suppose, for example, you search Google, and this is the exact information retrieval. You have a sentence, it will find the exact match on some web pages. And what GPT can do is it learn from the web scale data, and it can generate and predict next token. And it will, I think, it's still doing interpolation, because it's approximate information retrieval. It will generate something not exactly anywhere, but it still lies in the same distribution. So there are very simple examples you can take. You can test. So I think these generative models are still doing approximate information retrieval. Suppose, for example, you ask a simple question. So I have a graph of 5 nodes. This graph node labeled A, B, C, D, E, and what is the number of hops from node A to node E? And it will give you an answer, correct or not. But if you ask, I have another graph, 5 nodes, exactly the same graph, but you label them as 1 to 5 and not A, B, C, D, E. Ask exactly the same question, and likely you will get a different answer. So I think GPT is still doing pattern matching, approximation, information retrieval. So based on that, I will argue that, so essentially the unknown boils down to the question of if GPT can do planning, out of distribution generalization in terms of generation, if you can generate anything that is out of distribution, right? So that it can generate something that we humans do not know, which is not anywhere on the web, but it can do so. I think it's essentially bound down to the question if GPT can generate anything auto distribution. And I would, based on my limited knowledge, currently I do not see it can do OOD.
No, I think we can agree that when we speak of Gen AI, we're talking about something 16 steps past ChatGPT. So,
what is your point?
Actually, let me ask my point in a very specific next question, which I think somebody brought up as well. So this is something we've been working on. So we've been working on formalizing what is hallucination. So the point is as follows. I've given you a fact, let's call it F1. I've given you another fact, F2. Okay? And now you want to generate a fact, F3. You want it to be sufficiently new, because if it's not new, you're in the ChatGPT regime and nobody cares. Or maybe people care. But you want it to be novel, you want it to be new, but you want it to be correct. So the question is, given F1 and F2, good. So the notion of that was exactly my question. How do you argue that you can take two facts, F1 and F2, and generate F3 that you can reason to be not a hallucination? So, I mean, I can tell you what we think of, but that's probably all wrong. We think of closed sets and convexity and things like that, but that's a very mathematical description. What in your mind is Gen AI? This is the simplest example of Gen AI. Two facts, I want you to generate a third fact, which you know is not provably false.
No? Yes? Maybe? Okay, great. So as a scientist, I actually want it to be falsifiable in principle, right? So I do want to have the opportunity for it to be wrong, the third fact. And I would, and then I would verify its, so in science, right, we cannot prove that something is true. You can just have the falsifiability framework experimentally.
Maybe I didn't express myself clearly. You want to generate something that is not easily falsifiable. So yes, it may not be true. So a hallucination is something that is clearly falsifiable. A non-hallucination is something which may or may not be true. It may be true, but it's not trivially falsifiable. So we want to generate things that are either true or at least not trivially falsifiable.
But there should, this is where I think the question we need to settle before answering this question, are we talking about the scientific process or are we talking about the inference process? If we're talking about the inference process, we can then deploy the entirety of our logic inference rules within some knowledge framework. And then the only easy question is, what is our knowledge framework? And can we encode it as a set of inference rules? But if not, right, and that is the really hard thing to do, easy to say, hard to do. Within the science, we actually want it to be falsifiable within the theory, right, experimentally. And so then the knowledge guided part is how do we encode the theory? And that is a harder problem than encoding the knowledge, actually.
I'll bring in the others and see if they have an opinion.
From my perspective, I think the easy way to evaluate if your generated one is good or false is based on human evaluations. But if you cannot do that, then I think you can do some, because I'm from a logical reasoning background, I was thinking about using some like rules or something to give a simple example. There is some of the work trying to generate synthetic images to boost your dataset. For example, generating some airplane for some bare surface. Then if you can tell the synthetic data is wrong because, for example, the airplane cannot be on the water surface. The airplane cannot be on top of the tree. This is some logical rules. We logically learn that, okay, based on this, we can say that it's a... Yeah.
We can open this. I mean, we're going to run out of time quickly. So I do want to give everybody a chance to maybe chime in and ask questions. And it doesn't have to be limited to what we've talked about. Anything you might want to ask our distinguished panelists.
It's very interesting where your question about how do you know if I'm hallucinating or not? How do you So it's actually now turns into like a verification problem, right? So it depends on the domain that you're working on. So one way would be if it's math, you could probably have like a theorem proving verification system to check it out. And in your case, you know the physics of airplanes, so you can use that. So it depends on the domain, I guess, if the domain knows what's true or not. The interesting thing is, for example, in some domains, you don't know the true answer, where you actually have to then do experiments to verify. So, but it's interesting.
So I think when it comes to scientific domains that have laws, right? Laws which are conservation of energy, second law of thermodynamics, and so forth. I think if you come up, it's already a well established tradition in physics that you can have a model. So okay, a lot of these laws are sufficient, right? They're not necessary, right? So if you have an observation that doesn't violate any of these laws, then as far as the physics knows currently, it's admissible. And then if it seems like hallucination to you, then maybe you're discovering new physics, right? And I think that's one of the really great powers of generative AI. And as somebody who does physics, that's what is interesting to me. I think this framework, foundation models and transformer architecture, generates cases where we just may be able to actually discover new phenomena, maybe not new laws, maybe not new equations, but new phenomena that you've not encountered before.
That's a wonderful perspective. Thoughts?
And also, I'm very proud to be a member of the computer science community. And I think it is time because I think when I work with the domain experts, they often don't think computer science as science. But now I think it is time actually for the smart computer science people to provide inspiration for the domain experts. And I do believe I do believe we're able to help the domain science to identify unknowns. This is what I believe. So it's really the benefits is on two directions: the AI for science and science for AI.
Different thing. And so Jennifer mentioned verification problem. And this is where actually going to this computer science framework, right? We know that proof optimization, like any new solution is much harder computationally. It has much higher computational complexity than verification. And so maybe this is a good framework for us to really double down on the whole sort of reduction certificate and verification kind of theoretical approach for evaluating the value of hallucinations or sort of the quality of the embedding space in general by or a generative model by the verifiability of its hallucinations.
Questions.
So I have a general question where I try and differentiate between LLMs, as we know them, and foundation model architecture and algorithms. And we've been seeing, and even in the course of this workshop, we saw foundation models being built for time series, for geospatial data. I'm wondering whether we should be focusing on building foundation models from large-scale scientific data, and which may serve as a more useful tooling for scientific research versus just LLMs.
So thank you very much. And that was one of the questions. So let me just pose the question in a more, as it was posed to me here, because you've probably seen the question. So the question is, should we be thinking of more generalizable, scientific, generative models? And might such models exist? Or should they be specialized for every context? And how should we go about this?
Well, I'm going to add one model to the foundation model zoo. And in this case, the first foundation model for the tree of life, BioClip, that is taxonomy guided, image based, not LLM. I don't deal with LLMs by choice. But, so this is images and taxonomy, and this is being expanded to include species descriptions and many other aspects. So, and already it has really accelerated, particularly in, I'm told, the identification and understanding of beetles, because they're to quote, and I actually forget who it was who said that God had an inordinate fondness for beetles. So there is use, right? And then yesterday I was arguing that maybe we should, in general, have a benchmark for scientific foundation models, but and for weather and climate, at least for weather and hydrology and more generally earth sciences, we have natural benchmarks, because we can say, okay, we're going to give it data up to this point and then look at prediction, because most of the tasks are prediction. How do we do benchmarks, good benchmarks for other domains? So we're, Joseph is working on evolutionary benchmarks. We are trying to build biodiversity benchmarks, where scientific benchmarks, if you, let's say, read all of the literature up to 1993, I don't know why, but up to 1993, with all the data that existed there up to that point, can you then make, discoveries from that? Can you build, if you build a model, is it going to provide discoveries, predictions, and new theories that we know have been then discovered up to that point? So that would be a meaningful benchmark for me to test something that you're proposing.
Yeah, I think that's a great question. So I think we are doing AI for science, and the science is such a huge field. So for example, if you talk to physicists, you tell them I have an infinite computation. So whatever you give me, I can compute. Then most of the physicists will think you can solve most of their problem, because in their field, all the rules, etc., have been known for 100 years. So if you can solve all these questions, for example, if you can solve density function theory for proteins, for any of the materials, I think we solved a lot of problems. For example, so we are talking about material modeling, we are talking about multi-scale modeling, right? How to model material from atoms, quantum, even electrons at higher scale, etc. But the key is nature does not have a scale, right? Nature works without knowing the scales. I think the reason why we divide the scale is because we cannot solve this problem at the smallest scale. If we can solve every material at the quantum level, I think we do not need other levels. The reason is because we are limited in terms of our computing. But I think biology is very different. If you work with biologists, you tell them I have infinite computation. So they still think you cannot solve their problem, because all rules have exceptions in biology, except this statement, I think, right? So all rules have exceptions. So you still cannot solve their problem if you have infinite computation. I think AI for science is a huge area. I think we need to somehow treat them slightly differently in each area. And in that way, I think we can potentially build a foundation model for each of the sub-areas. For example, in my team, we are working on to build a foundation model for material discovery. The key challenge there is we need to identify a material with certain property, and it's a stable material. I think over there, we know the physics, and there's potential we can build a foundation model that can try to accelerate to the, for example, quantum mechanics, density functional theory.
Thank you. Let's just take two more opinions. And
who defines areas?
Yeah, I think that's a good question. Again, nature does not divide physics, chemistry, and mathematics. All these are artificial. I think that's a great question.
And then I want to take all the foundation models and combine them into one model to rule them all.
I think there's one question all the way in the back.
Yes. Yes. So, yes, I would like to make a few controversial statements. Basically, the topic of this workshop is about philosophical issues related to knowledge discovery and whether those issues can be addressed by machine learning. But the problem is that machine learning has no scientific foundation. 5 years ago, nobody knew about LLMs and transformers and so on. Now everybody is doing it, including politicians and business leaders and so on. But nobody can explain why they work. So the mode of operation in machine learning is that we have a bunch of heuristics that work for some applications. And we believe that we have certain beliefs. For example, one belief is that deep learning works better than any other method. Another belief is that deep learning imitates human intelligence because there are neurons and so on. But those are beliefs. It has nothing to do with science. So unless we have some scientific understanding of machine learning and even supervised learning, really it's premature to talk about knowledge discovery using machine learning.
Who wants to take that?
I would say one extreme view of machine learning would be the same as of all of math. It's a human construct that is useful. It's an abstraction that allows us to simplify the relationships in the world that is, to make useful inference about it, right? And you can define many different maths, and they will be useful in their own different ways, right? So that is maybe an extreme view that goes in the same direction of controversy. No?
When we talk about math, we talk about idealistic approach. And if we need to look back at the history of knowledge. Yeah. So initially there was idealism. That means that what matters is ideas and reality does not matter. Yep. Then we moved to materialism, which says that reality matters and ideas don't matter. Where we are now is data-centric view of reality. That simply means all that matters is data, and ideas don't matter, and reality doesn't matter. And this is where we are now.
And yet the philosophers were constantly surprised, just because we said that idealism, the philosophical approach of idealism and math is the outcome of that the only thing that matters is this idealistic approach. We're shocked just how useful it turned out to be for reality. Similarly, for realism, when all the theories of the realism turns out they're actually abstractable enough to describe abstract concepts and kind of start touching, or at least going towards in the direction of idealism. So who's to say that the data-centric realistic approach is not going to surprise us in ways that both are kind of useful in the idealistic sense or in the realistic sense?
No, I don't argue that it's not useful. It's very useful, but I argue that it's not scientific because there is no science.
It's philosophical. Okay. What's wrong with that?
Now we got a whole bunch of hands up. Here.
So Vladimir, I will give you the spatial view. GPS, we use the notion triangulation, right? So for example, if you want to understand history, the advice is read 3 different books, 3 different perspectives. And you have provided 3 perspectives to knowledge. Maybe the truth is in between. We should probably look at all 3 views. And if something holds up in all 3, it's probably more robust. Right?
Yeah, that's a really interesting question. But I would say there is some theory behind machine learning as well, and we're trying, as a field, as a community, we're trying to learn more about and understand it better. But in terms of like learning from data, actually a lot of science is about learning from data, right? You do the experiments to observations and then figure out what are the models that explains these observations. And so we start thinking about models like Newton's law, everything. We try it out and then experiment and repeat it to replicate. In some ways, machine learning is doing that, where given data, you try to automate learning these models. It's just so happened that now, like deep learning is really like a nonlinear approximator of like very complex regression models. In some ways, automatically learning that. So stuff. I mean, in some ways, that's what machine learning is doing. It's like a function approximator that is more complex. Yeah.
Which is a reductionist approach, right?
Yeah.
We're just a very, very high dimensional reductionist.
But then the key thing is that we keep on saying that in discovery, we have to work together, because it's not just the algorithm that or the ML person developing the models. We have to work with the domain scientists to figure out what are the right experiments to do, what are the right questions to do, so that we can make the discovery. We advocate, I think, as the KGML community here. That's why the knowledge guidance is important.
Well, I would argue that science does not come from data. That's why we call Newton's law, because Newton invented it. Science comes from human creativity.
Absolutely.
It has nothing to do with data. Data is used.
No, well.
No, nothing to do. No, I'm not saying nothing to do. But the primary source of knowledge is human mind.
Well, okay, great controversial statement.
No, let me continue, because humans don't need big data to learn. Humans learn with very little data.
Badly, to quote, to bring back the quote of what is simple, something and wrong, right?
Hey guys, we really are getting to a time when people have to leave for the airport. So I do want to thank everybody, namely the panelists, all of you guys. This was fun, and we could go on perhaps after we're done here. So thanks very much, and thanks once again to all the organizers. I had a wonderful time. Thank you.